Hello, welcome to KARURA. We are a team of 74 members based in Japan and the United States.
We are proud to present our readiness for the 2024 University Rover Challenge.
Several collaborative design decisions have been made in partnership with members from the US and Japan, resulting in a finalized design featuring a four-wheel configuration. The choice is geared towards weight reduction while facilitating the use of large 38cm wheels. This improves navigation over rough terrain and allows for higher ground clearance. The wheels are crafted through 3D printing and incorporate aluminum plates on both sides for increased rigidity. A rubber tread is wrapped around the wheel to increase traction and durability. The chosen motors are PID controlled by the main computer and exhibit high torque capabilities, provide necessary strength, and offer plenty of speed to successfully execute each mission.
The Rover features differential suspension. The design change from bird gearbox differential allows for better stability on flat and rough terrain, as well as mobility on slope of about 20 degrees. The chassis is constructed with an aluminum box frame and removable wall for ease of access. By dividing the enclosure to two sections, it allows for the main electrical component to stay in place, while allowing space for components corresponding to their mission to be swapped out. Our Rover has three forms for various missions. The team can quickly change components required for each individual mission.
The Rover, powered by 2, 3, and 6-cell lithium polymer batteries for its actuators, includes an e-stop button for emergencies. In addition, the computers operate on stable 5 and 12-volt mobile batteries. In mission modules, power inlets, LAN, and USB ports are all consolidated for swift exchange. Additionally, a communication tower with a 360-degree camera, GPS, and halo antenna enables communication at a distance of at least 1.5 kilometers, with LED lightings indicating manual control, stop, or autonomous movement.
Advantages of having an international team is that we were able to test many variables in our design efficiently, and this was evident in the final construction of the arm. What resulted was a 6-degree of freedom mechanism that has strength and dexterity to accomplish any task throwing at the Rover. Rover can transport heavy objects, flip switches, turn knobs, open drawers, and many more.
Our arm features 5 worm gears and 1 linear actuator. Worm gears allow for a simple braking mechanism with precise and effective control, while the linear actuator allows us to lift up heavy objects with great stability. The hand features sliding fingers powered by a ball screw and worm gear, providing constant power with the self-locking mechanism. Lasers and cameras are placed on the Rover for the operator's convenience at the base station. Our arm is controlled by sending coordinates in the workspace, so the hand can move to the target smoothly.
In the navigation mission, we divide development in 3 essences: GPS navigation, alcohol detection, and object detection. In GPS navigation mode, stereo V-SLAM generates 3D point cloud data, enabling precise cost map projection using SLAM-based odometry. The optimal path is then computed using the Dijkstra method. For alcohol detection, OpenCV is utilized to locate alcohol tag. Position estimation is based on the tag's size, tilt, and coordinate in the image. Object detection employs a DetectNet model powered by PyTorch, trained on the dataset exceed 2,000 samples per target using GoogleNet architecture. The Jetson onboard supports efficient parallel processing for these intensive image processing tasks.
Next, let's go to the science part. First, we search for locations for sampling using the high-resolution camera mounted on the Rover. Then, our proprietary morphology database and look database show key features of the habitable place. Checker cube indicates the scale of the terrain. The excavator system begins initiation analysis. It draws a drum, rotates it to dig by a hydraulic servo, adds solvent, mixes, then pumps the mixture into the slide analysis system. By deploying 4 excavator systems, analysis can be achieved without risk of contamination. The mixture is divided into 5 parts. 3 are used for chemical reactions, 1 for Raman spectroscopy and 1 for microscopy. For the chemical reaction, we use PCR assay, firefly luminescence, and Sudan 3 to detect amino acid, ATP, and lipid. Each reaction is induced in a cuvette and observed by a camera. To promote reactions, a motor vibrates the containers.
We use Raman spectroscopy for further detection of biomolecules. The laser is 532 nanometer to seek organic carbons such as lipids and pyrogens. The tip sensor type microscope does not require lenses and focal point, which is resistant to vibrations. Ultraviolet light on the specimen detects microorganisms, and we measure the scale and brightness of the sample. Also, we try to find microfossils by image analysis of roundness. After analysis, the Rover undergoes sample return, doing with the in-front earth auger and collecting subsurface samples with a rear Rover. The thermometer and soil moisture meter attached to the collector will investigate the subsurface condition.
KARURA is more than ecstatic to present our readiness for 2024 University Rover Challenge.